Alright, in this video we're looking at a review for chemical equilibrium. This would be useful to do before a test or before the final exam. It's aimed at Chemistry 40S students, but would also be a pretty good review for AP chemistry students as well. Just one note, if you are an AP chemistry student, there won't be any references in this video to equilibrium constants calculated using pressures, Kp. Okay, but that's not covered in the Chemistry 40S course. All right, so the first question, I'll give you a chance to read the question. And then I would suggest you pause the video, try it yourself, and then check your answers afterwards. So in an aqueous solution of potassium chromate, we have this equilibrium shown here existing, and we're told that we want to use Le Chatelier's principle to fill in the blanks below. So sulfuric acid, which has hydrogen ions in it, is added to the system and the color changes. Well, this is Le Chatelier's principle, so why don't we look at the expression for Q. Q is going to equal the concentration of dichromate divided by the concentration of chromate squared times the concentration of hydrogen ions squared. Now, if we were to add sulfuric acid, then we're going to increase the concentration of those hydrogen ions, which are in the denominator of Q. So that's going to make Q get smaller. If Q gets smaller, then Q will be less than Kc, because Kc is unaffected unless temperature changes. If Q is less than K, we know that causes a forward shift in the equilibrium. So we're going to see a forward shift as a result of adding those hydrogen ions. So the color change would change from yellow. It started off as potassium chromate, which is yellow, and it'll change to dichromate, which is orange. So we're going to see a change from yellow chromate to the orange dichromate. So the concentration of the dichromate ions, Cr2O7 is increasing, while the concentration of chromate ions is decreasing in that forward shift. Things on the left side will decrease in concentration, things on the right side will increase in concentration. And we just said that a forward shift will occur. Questions 2 and 3, give them a try. So question 2, a reaction that takes place in both a forward and reverse direction is said to be a reversible reaction. Products are formed when reactant particles collide, but then those product particles will also collide and form the reactant particles again. Question 3, the symbol Q is for the reaction quotient. So we just referenced that up above. When Q is greater than Kc, a net reverse or backward reaction will occur until equilibrium is reached. When Q is less than K, we saw a forward shift. When Q is equal to K, it means the system is at equilibrium. All right, now we have some true-false questions. Again, I would suggest pausing the video and seeing if you can do these yourself. So question 4, dynamic equilibrium, rates of forward and reverse reactions are equal. That's the definition of equilibrium, so that is true. Number 5, you need a closed system for equilibrium to be established, and a closed system just means reactants and products can't escape. That is also true. If reactant particles or product particles can escape, then the forward or the reverse rate will be affected by that. As a simple example, to consider an open bottle of water and a closed bottle of water. In the open bottle of water, it just keeps evaporating until there's no more water left. Because as the water evaporates, the water vapor escapes from the bottle, and the reverse reaction, the condensation reaction, just doesn't happen. But if you close the bottle, if you put a lid on the bottle of water, then now as the water evaporates, the vapor can't escape, so the vapor will begin to condense again towards the liquid water. So the reverse reactions rate will build up, and eventually the rate of evaporating and the rate of condensing are equal, and you've reached equilibrium. So you need a closed system for equilibrium to be established. Number 6, equilibrium concentrations of reactants and products are equal. That is false. We said back in number 4, the rates of forward and reverse reactions are equal, but it's rarely the case that the reactant and product concentrations would be equal. They're almost never equal. Question 7, when Kc is very large, products are favored. In other words, the reaction is said to be complete. Well, if you think of a Kc as being very simply a ratio of the concentration of the products divided by the concentration of the reactants, now that is an oversimplification, but it is a simplification. When Kc is large, what does that mean? It means that your numerator must be much larger than your denominator in order to get a large Kc value. That means you've got much greater concentrations of product than of reactants. So yes, the products are favored. And because you have so much product and very little reactants left, one of the reactants almost got used up, or maybe all the reactants got almost used up. Therefore, the reaction would be described as being almost complete. Question 8. If you hold the temperature constant, increasing concentration of a reactant would cause Kc to increase. Well, the key there was holding the temperature constant. The only experimental variable which would affect a Kc is changing temperature. If temperature is held constant, then the Kc value just doesn't change. So in this case, this would be a false statement. Okay, a few more true-false questions. Pause the video and give those a try. Question 9 says decreasing temperature for an endothermic reaction would cause the Kc to increase. Well, to answer that, remember the graph that we saw with temperature and how it affects Kc values. There was a graph for endothermic and a graph for exothermic reactions. For endothermic reactions, the graph looks something like that. Now, this said that decreasing temperature would cause Kc to increase. But as you can see in the graph, if you were to lower the temperature, the Kc gets smaller. So this statement is false. Question 10, saturated salt solution would be an example of an equilibrium. Well, earlier we used the example of a closed bottle of water with evaporating and condensing. Here we have a saturated solution where you have salt, which is constantly dissolving or dissociating. At the same time, you have the ions which have already dissolved or dissociated. They are precipitating back to the salt, the solid salt. So because you have those two opposite processes, the salt ions are dissociating and the dissociated ions are precipitating, they're happening at the same rate, which is why it looks like the salt is no longer dissolving. So yes, a saturated solution is indeed at equilibrium. Number 11, a catalyst increases the percent yield in a reaction. That's false. The catalyst would make you reach an equilibrium system faster, but the catalyst doesn't change the value of Kc and therefore will not change the percent yield in the reaction. Number 12, when writing equilibrium expressions, solids and liquids are left out because their concentrations are constant. Well, we know that solids and liquids are left out, but do you remember why we leave them out? This is exactly the reason. This is true. The concentration of a solid doesn't change. If you use up half of a solid in a chemical reaction, the concentration of the remaining solid is the same as the concentration of the starting solid. And the same would be true for liquids. So because their concentrations are constant, we don't include them in the expression for Kc. All right, we're now getting into some multiple choice questions. Number 13, pause the video and give that a try. So it says some SO3 is put into an evacuated flask, sulfur trioxide, and we can see in the reaction that that decomposes to make sulfur dioxide and oxygen. how do the rates of the forward and reverse reactions change as we approach equilibrium? Well, during the reaction, the SO3 that you put in is getting used up, so its concentration drops. While it is decomposing, it's producing the SO2 and the O2, so their concentrations will increase. Now, since concentration affects the rate of a reaction, the dropping concentration of SO3 means the forward rate will decrease, while the increasing concentrations of SO2 and O2 mean the reverse reaction would increase. So we're looking for a decrease in the forward reaction and an increase in the reverse reaction. Number 14, give that a try. So the chemist put some ammonia into a 2-liter flask. At equilibrium, there was 0.060 moles of nitrogen in the flask. The question is, what would be the concentration of hydrogen in the flask also at equilibrium? Well, we look up at the balanced equation and we see that the nitrogen's coefficient is a 1, while the hydrogen's coefficient is a 3. That means there's a 3-to-1 ratio hydrogen to nitrogen. So if we got 0.060 moles of nitrogen produced, we would get 3 times that, 3 times 0.060 moles. That's going to be 0.18 moles of hydrogen produced. Now, the question wasn't asking for how many moles, it asked for the concentration. Well, concentration is moles divided by the volume. So if we take 0.18 moles, divide by the 2.0 liters, we get a concentration of 0.090, which is choice C. Question 15. So for which of these reactions would Kc simply equal the concentration of oxygen? So in part A, we'll just go through each one of them. In part A, the reactants and products are gaseous, so that's a homogeneous gas phase equilibrium. Its Kc is going to have ozone in the numerator and oxygen in the denominator. It's not going to simply equal oxygen's concentration, so we can rule out A. In part B, the products are solid, the reactants are solid and gaseous, so this is heterogeneous equilibrium. We remember to omit the solids as well as liquids from a Kc expression. So for part B, the Kc would equal, products are all solid, so we'll just put a 1 in the numerator as a placeholder. In the denominator, the only thing we can include is oxygen because it's a gas, so Kc would equal 1 over the oxygen concentration. But we wanted Kc to equal oxygen, not equal the reciprocal of oxygen, so we can rule out choice B. Choice C, the water reactant is a liquid, so we would omit it from the Kc expression, so this Kc expression has no denominator. But on the right, the hydrogen and oxygen are gases, so we'll get hydrogen and oxygen in the Kc expression, so C is not the answer. That leaves us with D, and D has to be the answer. If you look at it, the oxygen gas is on the right-hand side as a product, while oxygen liquid is a reactant. Liquids are omitted, so for this, the Kc would equal the product, oxygen, over 1, or just oxygen's concentration, which is what we were looking for. Question 16. Pause the video and give that a try. So this question is going to require a little bit of calculations. We have a 2.5 liter vessel. Nitrogen monoxide, oxygen, and nitrogen dioxide are present at equilibrium, and we're told that we have a certain number of moles of each one. We want to calculate Kc. So we're going to use the formula C equals moles over volume, and we can say at equilibrium, the concentration of the NO gas will be 2.83 moles divided by 2.50 liters, gives me a concentration of 1.13 molarity. Doing the same thing for oxygen, I won't show my work, but oxygen is 1.20 molarity when you divide its moles by the volume, and the concentration of the NO2 the same way, N over V, is going to be 7.20 molarity. Now that I have all three concentrations, it's easy to calculate Kc. It's the concentration of the NO2 squared over the concentration of NO squared times oxygen. Plugging those three concentrations into the expression and then evaluating, we get Kc is very close to 34, so choice D is the correct answer. Number 17, pause and give that a try. So we're given the Kc 0.0045 for one reaction, the decomposition of N2O4. But we're looking for the Kc of a different reaction, and when we compare that reaction to the original, we see two things have changed. We've reversed the original equation to get this one, so the original equation has been reversed. We've also multiplied the original equation by 1/2. Where we used to have N2O4, now we have 1/2 N2O4. So we've multiplied by 1/2. So we remember that the way you balance an equation changes the value of Kc. So Kc here would equal, reversing means we take the reciprocal of the old Kc. So we'd say 1 over 0.0045 because we reversed. But if you multiply by a number, then you raise Kc to the power of that number. So in this case, we multiplied by 1/2, so we have to also raise the Kc to the power of 1/2. Now, raising something to the power of 1/2 is the same as taking square root. So either one of these would be acceptable. So grab your calculator and evaluate those, and you'll find out the answer is 15. So choice B. Number 18, pause and give that a try. Okay, that should be pretty quick. We've discussed this already. The value of Kc changes if you change temperature. Any of these other changes have no effect on the value of Kc, which is why it's referred to as an equilibrium constant. But it does depend on temperature. Change the temperature, you change the value of Kc. Number 19, pause and give that a try. So it's the same reaction we saw a moment ago, N2O4 decomposing into NO2 gas, and the Kc is 0.0045. The question says you put 0.25 moles of each of the two gases in a 0.50 liter vessel. As soon as I see moles and liters, the formula C equals N over V jumps into my head. The question is, which of the following would describe the change in concentrations as we approach equilibrium? And we're looking for the N2O4 increasing or decreasing, and the same for the NO2. So to answer that question, we basically have to decide whether the equilibrium up above shifts in the forward direction or shifts in the reverse direction. And to do that, we need to calculate the reaction quotient, Q. Q is calculated the same way as Kc, so concentration of NO2 squared over concentration of N2O4, but the difference is that for Q, we can put any concentrations into the expression, not just the equilibrium concentrations. So here we can take the 0.25 moles divided by 0.50 liters, and we get a concentration of 0.50 molarity for both the NO2 and the N2O4, which means the value for Q here is going to be 0.50. So right away we can see this was not at equilibrium because Q is not the same as the Kc up above. But more than that, we can see that the Q is actually greater than the Kc. And as we said earlier, that means a reverse shift will happen. If the equilibrium shifts in the reverse direction, then the NO2's concentration would decrease, because in the reverse direction it's a reactant, while the N2O4's concentration would increase, because in the reverse direction it would be a product. So we're looking for the N2O4 to increase and the NO2 to decrease, and that would be choice B. Question 20. Pause and give it a try. So this is ozone decomposing into oxygen gas, and the Kc is 36. What is the concentration of ozone if the equilibrium concentration of oxygen is 0.058? So the key there is that we're given the equilibrium concentration of the oxygen, and we're simply looking for the concentration of ozone that would go with that. So this is simply setting up the Kc expression. So Kc is concentration of oxygen cubed over the concentration of ozone squared. And we know 2 out of the 3 things in this expression. The Kc is 36, and the oxygen is what we're trying to find. The oxygen we were given. Let me just erase that. So the oxygen, I didn't need to erase that. The oxygen we actually know, so the oxygen is 0.058 molarity cubed divided by the ozone, which is what we're trying to find. Sorry about that. So now doing some algebra, the ozone's concentration squared will equal the 0.058 cubed divided by 36. And that gives me a value of 5.4 times 10 to the minus 6. Now to get the ozone's concentration, we simply have to square root to get rid of that squared symbol. So when you square root this number, you get 0.0023, which is choice A. Question 21. So we're looking for the mass of carbon dioxide that'll be present in equilibrium after you have 100 grams of the solid calcium carbonate that was put in a 2-liter vessel and allowed to decompose at a high temperature, and it reached equilibrium. What mass of carbon dioxide would be present? Well, we know the Kc value. Well, that Kc value, looking at the balanced equation, is actually equal to the concentration of CO2. The calcium oxide and the calcium carbonate are solids, so they don't get included in the Kc expression. That means the concentration of carbon dioxide is 0.100 molarity. So since we know the volume is 2 liters, we can use a couple of unit multipliers, or you could use 2 formulas. You could say C equals N over V, and since we know the concentration of the carbon dioxide and the volume, we could find the moles, and then we can use moles as the mass divided by the molar mass. Since we know the moles and molar mass of carbon dioxide, we can find the mass. Alternatively, we could use a couple of unit multipliers. We'll take the volume, 2.00 liters, and with one multiplier we'll convert liters into moles of carbon dioxide, and then with a second multiplier we'll convert the moles of CO2 to grams of CO2. In the first case, this is the concentration. Kc value is 0.100, so 0.100 moles per liter. And then the second one is our molar mass of carbon dioxide. 1 mole from a periodic table would weigh 44.01 grams. Grabbing a calculator and evaluating that, 8.80 grams of CO2 would be present. All right, questions 22 and 23 before we start looking at Le Chatelier's principle. Pause the video, read over the scenario, and try question 22. So in an experiment, we have 4 moles of SO2, 5 moles of oxygen. They're placed in a 5-liter vessel and allowed to reach equilibrium. When equilibrium is reached, 10% of the SO2 remains in the flask. So we know initial conditions, and we know something about the equilibrium conditions. That should have been a clue to set up the ice table. So I'm going to write the balanced equation again. 2 SO2s react with oxygen to make 2 SO3s. Everything here was in the gas phase. Using our formula C equals N over V to get concentrations, we can see the initial concentration of SO2 was 0.800 molarity, 4 moles divided by 5 liters. The initial oxygen concentration was 1.00 molarity, 5 moles divided by 5 liters, and there was no SO3 in the container. Now we were told that at equilibrium, so we go down to the equilibrium, the third line of the ice table, 10% of the SO2 remained in the flask. Well, 10% of 0.8 means 10 over 100, 10% of 0.8 would be 0.0800 molarity. So at equilibrium, there's 0.0800 molarity of the SO2. Now I can fill in the ice table because I know all of the initial numbers and I know one other number, in this case equilibrium. So the SO2, if it began at 0.8 and ended at 0.08, it lost 0.720 molarity. Oxygen would also lose because it's also a reactant, and it would lose half as much because the coefficient is a 1, while SO2 has a coefficient of 2. So half of 0.72 is 0.360, and the SO3 is a product, so it's going to gain, it's on the other side of the equation, and it would gain the same amount as the SO2 lost because the ratio there is 2 to 2 in the balanced equation. So it would gain 0.720 molarity. So then we have 0.720 molarity of SO3, and 1 take away 0.360, we have 0.64 molarity of oxygen at equilibrium. So from these choices, choice C is the correct answer for oxygen at equilibrium. We want to calculate the Kc. The Kc is going to equal the concentration of SO3 squared divided by the concentration of SO2 squared times oxygen. Plugging in the equilibrium numbers from the ice table above into this expression, we'll find that the Kc value is very close to 130. So with two significant digits, we'll write 130 as our answer. All right, so far we've seen equilibrium theory, definitions, the reaction quotient, and we've done some simple calculations with equilibrium. Another big topic in equilibrium is Le Chatelier's principle, and that's what we're going to focus on in the remaining questions. So question number 24, give this a try. 24 and 25 both deal with this equilibrium, but try question 24 to begin with. So there's two ways to approach Le Chatelier's principle. Some people like to approach it with kinetics, considering how the rates of forward and reverse reactions are affected. I prefer usually to use the reaction quotient to think of it. So looking at this question, we can say the reaction quotient up above is the concentration of carbon dioxide cubed divided by the concentration of carbon monoxide cubed. We leave out the iron oxide because it's solid, and we leave out iron because it's liquid. They don't appear in the expression for Q or Kc. So the question is, which of the following would cause the equilibrium to shift to the right? Well, equilibrium shifts to the right, shifts forwards, if Q is less than Kc. So anything that would make Q get smaller or Kc get bigger will result in Q being less than Kc. So we'd like Q to decrease, or we'd like Kc to increase in order to achieve Q being less than Kc. So let's see, the first choice says add more iron oxide. Well, looking at the expression for Q, iron oxide is not there, so that would actually have no effect on the equilibrium. Choice B says add more iron. By the same logic, iron is not in the expression for Q. Solids and liquids don't affect the equilibrium, so adding iron has no effect. But removing carbon monoxide, choice C, that would definitely change Q. Carbon monoxide is in the denominator of Q. If you were to remove some of it, then the denominator of Q would get smaller. If you have a smaller denominator, you're dividing by a smaller number, Q would actually get bigger. But we want Q to decrease. So we know the answer is not A, B, or C. Then what about choice D? If you were to remove carbon dioxide, well, that's in the numerator of Q. That would make the numerator smaller. If you have a smaller numerator, your fraction is smaller and Q will decrease, which is what we were looking for. So choice D is the correct answer. Number 25 says, when the system was cooled, the mass of iron oxide increased. And then we want to choose which of the statements below is true. And looking at the choices, we have to decide whether Kc would increase or decrease, and whether the reaction is endothermic or exothermic. Just to remind you of the balanced equation up above, so we're cooling the system, and it resulted in an increase in the mass of iron oxide. Does that cause Kc to increase or decrease? Is the reaction exothermic or endothermic? Pause and see if you can figure that out. Well, the first thing I would note is if the iron oxide were increasing, then there was a reverse shift in the equilibrium. We got more iron oxide by the reaction shifting reverse. Now, the reason a reaction would shift reverse would be if Q were greater than Kc. Now, we know that we're changing temperature, so that has no effect on Q, but it does have an effect on Kc. So if Q is greater than Kc, Kc must have decreased. At equilibrium, the two of them are equal, so if Q is now greater than K, K must have decreased. Now, looking at the graphs, we have one for exothermic situations and we have another one for endothermic situations. Let's just take a look at one of them. We'll look at the endothermic graph, Kc versus temperature. The graph does this. While exothermic, I guess I'll draw them both. Exothermic, Kc versus T, the graph looks like this. So we know that when we cooled the system down, Kc decreased. Which of these two graphs shows that? Lowering temperature causes Kc to get smaller. But I hope you focused on the first one. When you lower the temperature, the Kc's there will get smaller. So that means we have an endothermic reaction and Kc decreased, which means of those choices, we're looking at choice A. Questions 26 and 27. These guys refer to methanol being produced, methanol is CH3OH, by reacting carbon monoxide and hydrogen with the help of a catalyst. So there's the balanced equation. Pause the video and see if you can answer question 26. So this is, again, Le Chatelier's principle, which of the following would describe the effect of reducing the volume of the vessel, which creates an increase in pressure. We want to see what would happen to the yield, the amount of product being produced, and the rate of the reaction. Well, this is Le Chatelier's principle, so let me write the expression for Q. Q for this reaction would be concentration of methanol divided by the concentration of carbon monoxide and hydrogen squared. Now, we reduced the volume of the vessel. We know that concentration is moles divided by volume, so if you reduce the volume, a smaller volume, you get bigger concentrations. So the concentrations in both the numerator of Q and the denominator of Q would increase because the volume has been lowered. But what happens to Q? The numerator increases, the denominator increases, but do they increase equally? We look at the exponents in the expression, and in the numerator we see the only exponent is a 1, so we would say the numerator is first order, while in the denominator the exponents are a 1 and a 2, which means the denominator's order is third order. So since you increased all of the concentrations, all three of them equally, the numerator and denominator increase, but the denominator, which is third order, it's cubed, it would increase even more than the numerator. So the denominator increases more than the numerator. Now you have a bigger denominator than numerator, that makes Q get smaller. So Q will decrease. If Q decreases, Q is going to now be less than Kc, which creates a forward shift in equilibrium, and that means we're going to make more methanol if you have a forward shift. So the yield will increase. So we're looking for choice C or D, the equilibrium yield has increased. But what about the reaction's rate? In our kinetics unit, we remember increasing concentrations would cause the rate to increase also. So because we decreased the volume of the vessel, concentrations went up. That means the rate will also go up. So choice C, where the yield increased because of Le Chatelier and the rate increased because of rate's dependence on concentration. Question 27. Which of the following combinations describe the effect of removing the catalyst? Remember that reaction that we just discussed was helped by adding a catalyst. Well, we know that catalysts increase reaction rates. So if you were to remove the catalyst, the reaction rate would decrease. So choice A or B looks good. And we also know that the catalyst has no effect on Kc and no effect on Q. So the catalyst has no effect on the yield, the amount of the amount of product we'll get. So we're looking at choice B. There'd be no change in the product, the amount of product, but the rate at which you're producing it would decrease. Questions 28 and 29 deal with hydrogen gas reacting with iodine vapor. And we're told that the iodine vapor is a purple-colored gas, while the other two gases are colorless. So which of the following graphs would show what happens if HI was removed and then a new equilibrium established? Pause the video and see if you can figure that out. So all four graphs show that the HI's concentration on the y-axis is decreasing. Right? We were told HI was removed, so there'd be a sudden drop in HI. Looking up at the expression for Q for this, we get Q is HI squared over hydrogen times iodine. If you were to remove some HI, the numerator would get smaller, and that means Q would be less than Kc. We'd see a forward shift in equilibrium. In other words, removing some HI, the system is going to shift forwards and more HI would be produced. But here's the key idea. Although more HI is being produced, it will never achieve the original concentration before we removed some. So we removed some HI that caused a stress. The system shifts forwards to make more HI and relieve the stress, but it can't completely relieve the stress. So in the end, there will still be less HI than there was at the beginning. The graph that shows that is choice B, where the HI increased but didn't reach the concentration that it began with before the stress was applied. Question 29, what would happen to the color in the vessel as a result of removing HI? Well, we know that the reaction was shifting in the forward direction. As it shifted forwards, the amount of iodine vapor in the flask would decrease because iodine would be a reactant in that forward shift. That means we have less purple gas, and so the color of the gas would get lighter, right? It would fade a bit. So we're looking for something that says the color fades, which would be choice B or choice D, and it fades because of a forward shift that we just discussed. So that was choice B. Question 30, 31, just four more questions with Le Chatelier and then we're done. A chemist is studying the equilibrium. Nitrogen and oxygen make nitrogen monoxide at constant temperature, and there's a graph here that shows what happens over time. Based on the graph, which of the following would have occurred at time t? I'll let you just look at the graph. What occurred at time t during the equilibrium? Pause the video and see if you can figure that out. So your choices, nitrogen was added. Is that true? A and B both say nitrogen was added. So looking up at the graph, the nitrogen concentration suddenly spiked, while the other two concentrations didn't. So that means choice A and B, which say nitrogen was added, those are both reasonable choices. Choice C and D, which said the system was moved to a smaller flask, doesn't make as much sense, because if you had moved it to a smaller flask, all three of the concentrations would have suddenly spiked, not just the nitrogen. So we're looking now at choices A or B because C and D didn't make sense. So will there be a forward or a reverse shift? Well, we could answer that the same way we were doing earlier by setting up the reaction quotient and looking at that. But we have this graph right in front of us. So looking at the graph, we can see that after we added the nitrogen's concentration fell, and the oxygen's concentration fell. Well, nitrogen and oxygen are both reactants. So if those are decreasing in concentration, this must be a forward shift. And that means the NO's concentration should have gone up. And sure enough, it did. Now there's also some stoichiometry involved in this. If you would look closely, you should find that the NO increased by twice as much as both the N2 and O2 fell. The balanced equation ratios are 1 to 2. So looking at this, we're looking for nitrogen being added and a forward shift occurring. Number 31, pause and give that a try. So if you recall, the question began by telling us that this was happening at constant temperature. If temperature is being held constant, then Kc does not change, right? Kc is only changed if the temperature changes. If temperature were held constant, Kc should not change. So choice C is the best answer there. Number 32. Pause and give that a try. So what is the effect of increasing temperature on this equilibrium? Looking at the balanced equation up above, we see we're also told the enthalpy change, the heat of reaction, delta H, and I see that it's negative. A negative delta H means that this was an exothermic reaction. So right away I'm going to recall that graph we saw earlier, exothermic. Kc changes with temperature, and it changes like this. It drops as temperature is increased. So here we had an increase in temperature, which means Kc should have dropped. So Kc falls when the temperature increases. If the Kc fell, Q is unaffected. That means Q is now bigger than Kc. Kc got smaller. And that caused a reverse shift to occur when Q is bigger than K. So the equilibrium will shift reverse or left, and Kc gets smaller. So choice B is the correct answer. And that brings us to the last question, which is not a multiple choice question. We have the Haber process, named after Fritz Haber, a German chemist, who figured out how to synthesize ammonia, NH3, from nitrogen and hydrogen gases. We have an equilibrium system with all three of those gases inside a sealed syringe. So you can see here the syringe with all three gases present. There's a plunger which can move in and out of the syringe, but the rubber cap prevents the gas from escaping. So we also notice that the reaction for the synthesis of ammonia was exothermic. The delta H is less than 0, which means it's negative. So this is an exothermic situation, just like we saw earlier. So let's sketch the graph again. Kc and temperature for exothermic situations does something like that. So we want to put check marks beside any modification that would increase the yield, a greater yield of ammonia. So we want this equilibrium to shift forwards to make more ammonia. So let's write the Q expression. Q is going to equal the concentration of ammonia squared over concentration of hydrogen cubed and nitrogen. So with the Q expression and the graph for Kc and temperature, see if you can figure out which of these changes would cause a greater yield of ammonia. In other words, a forward shift in equilibrium. So the first two choices, we have to decide whether we should add or remove nitrogen. Well, if we want the reaction to shift forwards, then we want Q to become less than Kc, which causes a forward shift and more ammonia to be produced. So if we want to get Q to become smaller, so Q is less than K, should we add nitrogen or should we remove nitrogen? Well, nitrogen is in the denominator of Q. So if you were to add more nitrogen, the denominator would get bigger and Q would get smaller. So the first choice there to add more nitrogen looks like a good choice. Hydrogen, should we add or remove? Well, this is very similar. If you were to add more hydrogen, hydrogen is also in the denominator of Q. So adding hydrogen would make the denominator bigger. That would make Q get smaller. Q would be less than K and a forward shift occurs. So adding hydrogen also looks good. Should we warm or cool the system? Well, we want Q to become less than Kc. So far we've been doing that by making Q get smaller, but if we change the temperature, here we're going to warm or cool it, temperature affects the value of Kc. Looking up at the graph above, we want Kc to be bigger than Q, so we want Kc to get bigger. We want Kc to increase. While in this graph, if you were to lower the temperature, the Kc gets bigger. So we want to cool the system, not heat it. Should we reduce the volume or should we increase the volume? Push the plunger in or pull the plunger out? Well, this one's a little bit more complicated. Why don't we just try one? Let's reduce the volume. If we reduce the volume, as we saw earlier, all of the concentrations would increase. So both the numerator and the denominator would increase. But just like before, the denominator here has a bigger overall order. Its overall order would be 3 plus 1, looking at those two exponents. So it's fourth order in the denominator, while it's only second order, the ammonia is squared in the numerator. So while both would increase, the denominator would increase even more, and Q would get smaller, which is what we wanted. So yes, reduce the volume should work. And the last choice, adding a catalyst, would that increase the yield? Well, we discussed that earlier. Adding a catalyst has no effect on Q and no effect on Kc, so the catalyst has no effect on the yield. But it would make the system reach equilibrium faster, but it won't change the yield of the ammonia. All right, so that's it for a review of equilibrium. This should be a good review for both test and for the final exam. If you're an AP chemistry student, be sure you also check out my YouTube video, which has equilibrium review questions specifically for advanced placement chemistry.